Right, since we didn't get a chance to do a lot together in class. So let's see, this is problem 3. First two, there is no tricks to them, it's just definitions. So look at this one here. Okay, so big deal here is the lever arm and the angle. And, well, in fact, if you get the lever arm, then you're sort of guaranteed that you have the right angle. That's the part of lever arms, the point of lever arms. So if I have, let's say I have some rope pulling on this like so, right? So what we have to do is, let's see, oh yeah, it works, great. You take yourself a ruler, and then that's good enough for this problem. And then let's pick another color to distinguish them. And then we need to extend the force line back. And so here is something interesting. This ruler tells me an angle right off the bat. 24, we need to get right angle to that. So we just have to add 90 degrees to 24, which will get us to 114. Oh, it doesn't work. Okay. That's all right. 24 and 66 makes 90. And then it passes through the rotation point, which isn't always the middle. And so, of course, you need some way of knowing the length of, where's the cursor? Oh, way down there. So now this is a right angle, and there's our force. This is our R. And now we have our R cross F, and RF, and its sine of 90 because of the way we set it up. Now, so of course now you need to know what is the length here from this point to this point. This is the magnitude of R. And you have to have some way of figuring it out. Maybe there is scale drawing, or they have a grid, or they give you X, Y coordinates, etc. Okay, so let's see what's next here. Oh yeah, so in this problem, you have these distances, and so you extend the F's, and then figure out what's the perpendicular distance from the rotation axis here. And they put it in the middle, so it gives you the chance to figure it out. I mean, they could have put it like, they could have said 1/3 of the way, but they put it 1/2 of the way. Okay, let's see what's part, next, okay. This is from computing due to applied force. Right, so this is about, let's see, turning it into the radial, and they call it parallel, but that means parallel to the direction that the object would be going. And let's see, snip, and hopefully this won't become too pixelated. And now let's make us a new slide. Nice. Okay, so we went over these two techniques in class, and I'll squeeze them onto one slide. Here we go. So the first technique is to, I don't know if I can find the cursor. So then you find out what is the radial component and then what is the tangential component. Sometimes they call it the parallel component. So you can see that F radial equals to F, and that's cosine of theta. And then that means that the F tangential has to equal F sine of theta. And then we have that, then we see that that angle is 90 degrees. So R cross F becomes R cross F tangential, which becomes F sine theta times sine of 90. In the technique that I prefer, you take your ruler, and it's similar to vector addition, and you slide your F vector. Since it's R cross F, you always slide the second one down. And then now you can draw it here. And let's get rid of the ruler. And depending on the situation, you may need to measure carefully. And then let's see. So this one here is fairly straightforward because of the way they gave us the angle. And now we have R cross F equals to RF sine of theta. And you notice that it's essentially the same. I just think this is easier, and you don't necessarily have to draw the line like that. On an exam, I would give extra points for it, but now you see R, give me a minute, R cross F, yeah, and so now the torque vector is into the page, even though, and this is just defining your space. That's nice. They don't usually do this. Positive direction is to the left. But that, you already knew that because you have your X and Y axes arranged. And then you see, oh, wow, of course, right-handed coordinate system, so counterclockwise is positive. Okay, let's go to the next one. It's a new slide. Where is it? Here we go. Excuse me. Okay, next. Enhance with uniform disk is, the disk is initially at rest. Okay. Copy. And oops, that didn't work out very well, did it? Paste. There it is. All right. I don't think it matters what is the horizontal or vertical, but you never know. And yeah, they always make this mistake where they put a space in between the number and the units. Okay. So I'm going to just take that to mean that I can draw this like so. And they didn't tell us exactly whether it's being pulled from the top or the bottom. Nope. Okay, so that means that we don't know which direction the torque vector is going to be. That's text effects. So we don't have to worry about that. We just know that we have this thing. It has an axle in the center. And let's see if it'll tell me yeah, there we go. And pivoted, and we say, we have a force tangent to the rim, so that makes it fairly straightforward. And so if it's tangent, then we know automatically that the, let's get rid of that. We know automatically that we can draw a lever arm. And so, there it is, RF, and I leave it to you to figure out the rest. Okay. What is it? What do they want now? What is the magnitude of tangential velocity? Oh, okay. So this is, you need to use the magic equations. I don't know if I'll get all of them here. I'm doing it off the top of my head. And then there's omega equals omega 0 plus, alpha t. And remember there's one with theta squared and or omega squared, right? There's 4 of them. You have to look those up. And then you have to remember tau equals I alpha. And you can look up the I for a disk on a table. Okay, let's see what's next here. Yeah, so tangential velocity, you have to remember v equals r omega and a equals r alpha, those kinds of these. All right. And each side. So how long have we got? 12 minutes. Okay. What's next? And that's it. Okay. All right. What's next? Okay. What constant torque is, right, to bring it up to an angle? Okay. That's fairly straightforward. They give you I. So that's sweet. Copy. Paste. Oops, redo that one. I should have learned my lesson last time. There we go. Oh, it's the same problem? Wait a minute. Yeah, I didn't hit copy here, I bet. Okay. There we go. So, this is a very similar problem. And you need the magic equations. And then you need the Newton's second law for this. And of course, they gave you I, so that's nice. And what else? Let's see. Yep. What's next? Which is fine. Oh, so you watch a video and then you make an answer. It's nice. It's concept practice. What's next? Yeah. Rolls down without slipping. Okay, so that's keywords. Remember, you're always looking for keywords. And let's see. I want a new slide. That's what I want. And did I copy something? Yeah. All right. 32 degree slope. Okay, so where's the math? So the without slipping is important. And so that means that V equals R omega, A equals R alpha. Let's see, hollow mass and They didn't give us a radius. Find the acceleration. And how spherical rolls down. Wow, interesting problem. Okay. There's the cursor. So we have angle here. That's touching. And we've got, right, okay. But it doesn't tell you the size of it. Interesting. But we have W parallel. And the torque is about the contact point here, R. And I'm going to pause this for a moment. Okay, so lo and behold, I clicked on review. I clicked on this here. And pretty sweet here. I looked it all over. And, this is for the yo-yo. I thought So what is C? Let's see, instructor. What shape reaches the bottom? Well, it would be the solid sphere, we know. You can express, C is diffraction. Oh, sweet. So here's the answer right here. I thought I had to do conservation of energy. And so you just look up, C. So all the I's have mr squared, right? That's the definition. So depending on geometry is the value of C, which is just the fraction in front of it. And here it is. See, ICM equals CMR squared. So you just go to a table and find for a spherical shell. That's pretty funny. Well, of course, they asked for, let's go back, see, to the review. So that's the V center of mass. And, here it is right here. And so, here it is, guys. So you just have to put, this is the wrong value of C right there. So you, all right. So you just have to make sure and plug in the right coefficient right there. And there's your answer. You see, there's more than one way to skin a cat, but then this is why you have to have this in your notebook for an exam. Okay, let's go to the next problem. Minimum coefficient of static friction, right? So you'll find the torque, and if you find the torque, but you don't know the radius, huh? So I'm not sure. But you can. I'm going to request the answer, but I'm not going to show you guys. So what I'm thinking is that part D is, all right, so you could come up with alpha, and you know T equals I alpha. I get it. And torque is also equal to RF, and you can just assume that angle is 90, and this is CMR squared, and this is alpha could be A over R, and then, yeah, well, R here, oh yeah, see, and then the R's cancel out, that's what I thought. And then then you know the force you need, and so, well, of course, that's pretty dumb. This equals the W parallel, but so you knew that. What you gonna gain out of this? So you don't even need any of that. You know that the W parallel, so you just need to know what W perpendicular is, so you can get the normal equals the W perpendicular. Okay, you guys know the rest. All right, what's next? Problem 9. In the form of solid cylinder. Okay, how are we doing? 22 minutes. New slide. Okay. Copy. All right. What constant torque? Copy. Yeah, we didn't get to these in class. So this is pretty straightforward. Yeah, you need your magic equations, and you have T equals I alpha. So, excuse me, you angular speed. Oh, okay. So omega equals omega sub 0 plus alpha t, right? Yeah, so you can get alpha. So that's the magic equations. And you can get alpha average. Stare at what they give you and you'll get it. And then you go here, and then you have to look up I on a table. What's next? What angle? Okay. So if you know alpha, you know T, you know omega 0. So then you have your you have one of the magic equations. And there's more. And use equation, the work. Oh, okay, so you know tau, use equation. Oh, so that's your delta theta. What is rho? Oh, okay, and that's remember the rotational kinetic energy equals I omega squared. Okay, let's see what's next. And Question 10. Is rim of large harder? Is it? Okay. 110 pounds, I think. All right. All right, what's the question? Calculate the total, assuming that you can treat the woman as a point. Okay. So this one exploits the scalar nature of the angular, the moment of inertia, and so we have this rotating disk, and we also have a point mass on the rim. And because it's a point mass, it's just an infinitesimally small point right on the rim. So then that means that the radius is just the radius of the circle. So you first need I equal to I disk plus I woman. And this is just mr squared. And well, let's make absolutely certain. Review. Well, that's not what I wanted. I wanted to know what the angular momentum of point mass is. Let's see. Yeah, it's just mass times radius squared. Okay. And then angular momentum equals I omega, which is a vector quantity, but this is a vector. So if it's going counterclockwise, it means the vector is pointing out at you. Okay. Oops. Homework. And let's get rid of this. No, can't get rid of it. That's just it. Okay. Question 11. A small block is a mass extension. Interesting. There's just one. Oh, there's a whole bunch of parts. Why does it do that? Okay. So let's do snipping tool instead of copy paste. And all right. It's a mass and it's attached to a massless cord passing through the block a distance from the hole is angular. What is that I'm seeing? It does look like matters. Is the angular momentum of the block conserved? Well, if I pull on it, but momentum Oh, so this is the same as pulling your arms in. So I would have to say yes. This is not intuitive. Yeah, and also just because I know momentum is always conserved. It's a good question. What's the new angular speed? Okay, so what happens is you have momentum equals I omega, right? So that means that I1 omega 1 equals I2 omega 2. So this, for part B, um, you I is equal, well, in this case, it doesn't matter what part you're doing, mr squared. So what you're going, if you make, you're going to make r smaller. So I2 is less than I1, so that implies omega 2 is greater than omega 1. So you figure out what's the change in, so you have, okay, so you start out with R equals 0.300 meters, R2 equals 0.150, but remember, since it's squared, it isn't half as much. You have to figure out that difference. Find the change in kinetic energy. Well, then you know everything now because now you have I1, you have I2, and you have omega 2, and you have omega 1. And I don't know. I don't think kinetic energy will be conserved, but you'll have K1 equals I1 omega 1 squared, and K2 equals I2 omega 2 squared. Okay, how much work? Yep. See that, remember that, and then for D, that would be work equals delta KE. It seems to me you have to do work in that case. Yeah, when you're on the carousel with your arms, I guess you don't do, it's interesting. You don't do work. Well, you see, if delta K is equal to 0, the work is equal to 0. Okay. Okay. Copy. And let's paste. Diver comes off board with arms straight up and legs giving her a moment of inertia. Okay, so they give you I1 equals 18 kg meters squared. I2 equals 3.6 kg meters squared. And then we see that delta theta equals 2 complete, so 4 pi, and t equals 1.0 seconds. So you see you can get omega bar, for example, delta theta over delta t, right? Okay, so let's look at what they want. If she didn't, if she wasn't tucked at all, how many revolutions in 1.8 seconds? Interesting. Okay. So 1.8 seconds. What? Oh, okay. I know what to do. So the first thing you need is angular momentum. And this is going to be I2 times omega bar. And then to get her, you want to find out what is her I1, and so this is 2, and that has to equal to L. So then you'll get omega bar 1, and then you just multiply it by 1.8 seconds. Okay, good luck.